Okay, hey everybody. So today we are doing topic 15, but before we get into that, just to remind you all, I put the project pairs up on Slack, so reach out to your project partner. Hopefully by today, if you don't hear from your project partner, if someone's not responding to you, let me know. So in preparation for the project, as I mentioned, you do have the option of choosing your own data set for this project. You don't have to if you don't want to, but you have that option just so, you know, if you're not interested in housing data, you can do something else. So I've already linked the project guidelines. There's a lot on this document, so don't worry about that for now. For now, just to get a sense of the dates that we're looking at for this second project. But mainly what I'm going to talk about today to start is just sourcing project data. So there is a provided data set, and that provided data set is on King County housing prices. King County is a county in, or is one of the counties in Washington State. I think it's the one that includes Seattle. And then, yeah, so that's what the data set is provided. The provided data set, it's about that project. If you choose to do the prescribed project, it is predicting the price of a house in King County using features like bedrooms, number of bathrooms, square footage, things like that. So just to get an idea of what kind of project we're doing and what kind of data you should be sourcing for this project. So I recommend Kaggle for just ready-made data sets. I don't think you have to go through the trouble of like using an API or web scraping, but I mean, by all means, if you would like to, you can. Kaggle just has a lot of pre-made data sets. So for example, I actually pasted the link for regression data sets. So all I did was plug in the search term regression, and there are a lot of different ones. So actually this is our project data set. But there's a bunch of other things, car price prediction, let's see, salary prediction, perhaps, a lot of different ones. Let's just go to page 9 and see what's in there. Maybe you want to predict something like sales. The whole idea behind this project is you're going to use features of something to predict something else. In terms of constraints for this data set, at least 1,000 rows and 10 columns. And this is prior to data cleaning. So if you find something, you end up dropping a lot of data, don't worry about it. Of course, you don't want to drop too much data. So maybe you want to do some inspection at the start. But at least 1,000 rows and 10 columns for this data if you're looking to source your own. So keep this in mind. The goal of this project is to predict a continuous variable. So something like the price of a house. Something else that you can think of is it doesn't have to be like an unbounded continuous variable. So for example, I remember my phase 2 project from many years ago was predicting a percentage. So between 0 and 1 and a percentage in between. So as long as it's continuous, that's what you can predict. So through maybe look at the data set that's provided if you want to get an idea of what your data should look like. But a lot of these data sets, not all of these are going to work. So if you have any questions about it, or if you just want to, I would say if you're not using the provided data, you have to let me know and have your data set approved by me first. So if you just want to send me any data sets that you're interested in to get my thoughts on them, feel free to do that. Any questions about the project data set? As of now, we haven't really talked about what we're going to do with the data set, but as of right now, things that you can start doing, you can start your data cleaning process. You can also start your EDA process. We, of course, I mean, not of course, but we are going to get into some like linear regression specific EDA. I'm going to talk about that next week, but for now you can do a very preliminary EDA and also just familiarize yourself with the data, familiarize yourself with whoever you're working with. So yeah, any questions regarding this? Okay, I'm going to make a note somewhere that if you are deciding to go with the not provided data set, just let me know because I have to approve your data set before you start working on it, just in case you go down a rabbit hole that will not work. Okay, and then when the time comes, I'll be talking through all of these other things in this document. You do have edit access to this document, so careful about like changing things, mainly because I have this like question and answer section that I've used for like, I think this document has questions from, I think, 3 past cohorts. So you'll have a lot to go off of. But just careful that you have edit access, that you don't just change or delete anything that's important. Okay. Other announcements, the feedback survey that's on Slack, and then also don't forget to work on your blogs. For those of you who transferred into this cohort, if you could do me a favor and just submit your blog on the phase 1 link as well, that'd be super great. Okay, so Project 2 guidelines will be going through this document over the course of next week and then the week after, of course. Okay, questions before we get into today's material? All right. Okay, so today is going to be the last slideshow for a while. Tomorrow we're going to get into our Jupyter notebooks again, so looking forward to that. But we're going to just finish off statistical power and some other statistical tests. So today we're going to talk about, again, statistical power, and we're going to go through 3 other tests: Welch's t-test, the Kolmogorov-Smirnov test, and ANOVA. So to start, statistical power, this is something that I sort of started talking about yesterday, but here are more solid definitions. So the power of a test can be defined as the probability of rejecting the null hypothesis when it is indeed false. So correctly rejecting the null hypothesis, correctly identifying that there is an effect. So if you have a power of 1, it is a perfect test that always correctly rejects the null hypothesis. This is directly related to beta, because power is always 1 minus beta. And if you remember, beta, which I talked about, I think yesterday, is the probability of a type 2 error, which is failing to reject the null hypothesis when it is indeed false. So after selecting an alpha, you can typically determine a threshold to maximize the power of a test. So I want to show you all this resource real quick. Tomorrow, I'm actually going to go over a coded example of how you will actually make use of statistical power. So I guess another loose end, but important to remember this definition for tomorrow. It's just the probability of correctly rejecting the null hypothesis. Now let's take a look at this resource. So I kind of alluded to this yesterday because we also talked about effect size. Where is effect size? Oh, effect size is D. Basically, these 4 variables, power, alpha, N, which is the number of observations in a sample, as well as D, Cohen's D, which is standardized effect size. These are all related to each other in a sense that you can set 3 of them to be whatever values you want. You can solve for the other. So for example, let's say I want to solve for power. If I set my significance level at 0.05, I have a sample size of 20. I want to choose this effect size of 0.63. My power is 20%. And let me just zoom out so we can adjust and see these results at the same time. If I change my alpha, you see that with a stricter alpha, the power goes down, laxer alpha, power goes up. But alpha, usually we're constrained at 0.05. If I increase my sample size, power also goes up. The way of thinking of this is the more data points that you have to go off of, the more confident you can be in your conclusion. And then finally, effect size. We'll talk about this in more detail tomorrow, but when you're designing an experiment, let's say you're doing like a drug trial, or maybe you're doing like COVID vaccine trials, for example, you're going to have, let's say, a number of, I don't know, number of antibodies, is that a thing? There's going to be a set number of antibodies that you're going to determine as enough. And so that kind of determines your effect size. So if you set a lower effect size, power goes down, higher effect size, power goes up. All right, just because if your effect size, the intuition behind this is the difference between your means, the greater they are, if you observe something that is of that difference, because the difference is so large, you can be more sure that that difference actually exists and it's not just spurious or not just occurring by chance. But we'll see this in action tomorrow when I go through a coded example of designing an experiment and looking at the power of a test. So going to be another little, we're going to put a pin in this for now. But based on that, any questions at this point? All right. We're going to talk about a bunch of statistical tests. So that's what the rest of this PowerPoint slide is. So yesterday we talked about the two sample t-test, which is a very, very common, I would say one of the more common statistical tests used by data scientists just because of A/B testing, and we'll get into A/B testing tomorrow as well. There is another two sample t-test that is pretty similar, but slightly different. So yesterday, the t-test that we talked about more specifically is known as student's t. We normally just refer to that as just the regular t-test. There is a variation on that t-test known as Welch's t. And the main difference is, and the main variation that it takes into account, is it takes into account different sample sizes and unequal variances between samples. So if you remember our example from yesterday, I'm not going to go through an example with this because they're very, very similar. If you remember our example for yesterday, we had a control group and an experiment group. And it was for, I think, like fat content in something. Anyways, one group was given the drug, one group was given a placebo, and we wanted to see whether the difference in the result is statistically significant. So exactly the same setup. However, our example yesterday, we had, I think, 20 or 25 subjects per group. So the groups were of equal sizes. And we also assumed the same variance within each group. So Welch's t just takes into account that it can be of different sample sizes and also of unequal variances. This is how you calculate the t-statistic and how you determine the degrees of freedom. Again, not important to remember this just because you'll see in the one line of code, it actually does it for you. So just know that the calculation of each statistic and degrees of freedom is slightly different. Therefore, you might get slightly different results. If you have the same sample size and same variance, you can use Welch's t and you'll actually get the same result as if you were to use student's t, if that makes sense. So just be aware that there are two different kinds of two sample t-tests. When in doubt, I would say just use Welch's t-test, which is actually I have the one line of code in that PDF table summary that I have on the homeroom. Okay, questions about this t-test? I'm not going to go through an example for this because it's pretty much the same example as yesterday's. All right. So just to summarize the 4 statistical tests we've seen so far, we've seen 1 sample test and 2 sample tests. So 1 sample test, an example of that is you're comparing a sample to an entire population. For example, does tutoring have an effect on the IQ of a group of particular students? You can either do a 1 sample z-test or a 1 sample t-test, depending on if you know your population standard deviation or not. If you do know your population standard deviation, like if you remember last week, we talked about this example, we knew that the population's IQ had a standard deviation of 16, then you would use your 1 sample z-test. But if you don't know your population standard deviation, and this was the example that we had with the sales training, they did not provide us with a sample. They didn't provide us with a population standard deviation. So therefore we used a 1 sample t-test. So these are 1 sample tests. Now 2 sample tests are 2 samples just different from each other. Very commonly used examples. For us, we're going to go through an A/B testing example tomorrow. So A/B testing you can do with a 2 sample t-test. Drug effectiveness testing, where a group takes the placebo, a group takes the actual drug, 2 sample t-test as well. And which 2 sample t-test you use depends on the samples that you're using. If they have the same size and variance, you use a regular 2 sample student's t-test. And if they have different sizes and variances, you use Welch's t-test. So that's just a summary of all the tests we've talked about so far. We have 2 other tests that are coming up in this presentation that are slightly different, but I think these are the main ones to be just aware of. All right, let's move on. So the next test we're going to talk about is the Kolmogorov-Smirnov test. So all the tests that we've talked about so far, like all 4 of these tests, has some sort of normality assumption. What does that mean? It just means that we made the assumption that the population just is normally distributed. I mean, a lot of things are like pretty similar to a normal distribution, but we just made that assumption straight up. We made the assumption that, yes, we have a mean and standard deviation and the population does follow some sort of normal distribution. So sometimes you want to just make sure of that or check for that. And so The normality assumption is something that is going to carry forward into linear regression. So good to remember that a test exists for that we can test whether something comes from a normal distribution or not. So what we have here is the one sample Kolmogorov-Smirnov test, which I'll just shorten to KS test. It's also called the KS goodness of fit test as well. And essentially what this test is doing is it is testing for the similarity between a sample and a normal distribution. And it's testing to just see how similar are the distributions in terms of the difference between their CDS. And I'll get into this in a little bit. So the idea here is if we have, let's say, a sample of 50 observations, we have 50 observations and we want to know, okay, is this group of observations normally distributed? Because if they are normally distributed, you can kind of guess that, all right, the population might be normally distributed as well. So to do this, what we do is we compare their CDS. So if you remember what CDS is, it's the cumulative distribution function. And how we determine that just graphically, imagine here, we have two lines here, one of them being the distribution. So let's just say that this solid line is the distribution. In this diagram is not really labeled, but let's just assume that our sample is this solid line over here. We're going to compare that to the CDF of a normal distribution, which is going to be this dotted line. So let's just take a look at what the CDF of a normal distribution looks like. So normal distribution, CDF. So let's see if there's a good image somewhere that we can use. Okay, so the normal distribution, CDF, cumulative distribution function, looks something like this. It's sort of like an S-shaped curve. And it always starts at 0 and ends up at 1. Remember that any CDF starts at 0 and ends up at 1. So therefore, if you're doing a KS test and you're plotting these results on a graph, both lines should start at 0 and end at 1. And here we want to compare to see how similar the distributions are. The test statistic here, and we'll get that. Actually, let's take a look at this. Before we get to test statistic, let's talk about the hypotheses first. So the null hypothesis is that there is no difference between the distribution of the sample and a normal distribution. So if you don't reject your null hypothesis, that's saying that your sample that you're testing for is normally distributed. So in this case, it seems a little bit like the opposite, but basically if you have a higher than 0.05 p-value, then you can say, okay, cool, my sample follows a normal enough distribution. The alternate hypothesis here is that there is a difference between the distribution of a sample and a normal distribution. So your sample is not normally distributed enough. And what other distribution it follows, this test doesn't really tell you that. So following our same statistical testing process that we did before, we set up our hypothesis. We know that this test, we're going to do a KS goodness of fit test. We set our alpha at 0.05. So for the KS test, the test statistic is actually pretty interesting, and I think it's kind of intuitive as well. It is the maximum difference between the two CDFs. So if we go back to this graph, this solid line represents our sample, and then this dotted line represents something that was sampled from a normal distribution. So the maximum difference is if you draw a vertical line down, you're actually getting the difference between the CDFs. So the test statistic here is whatever the maximum difference is between CDFs. So in this case, if we draw a bunch of vertical lines like this is a difference in the CDF. This is also a difference in the CDF. And then this D value over here is the maximum difference. So this is actually the test statistic that we're using for this test. Again, you can also code it out automatically. You don't have to calculate this. You don't have to plot everything and find the difference, but also just good to know intuition. Cool. So once you get that D statistic, you can actually look up, similar to how we use the T table, we can look up critical D values from the KSD table. So if we open this up, let's just say that we're doing a alpha of 0.05. Depending on how many things there are in your sample, you just compare your D statistic. So for example, 0.05 here, let's just say we have 20 20 observations in our sample, the critical D will be 0.29. So basically the difference for critical difference has to be, has to be greater than 0.29 to reject the null hypothesis. So the greater the number, the less likely it is to be normally distributed. So that's also an intuition to think of. Or using SciPy, you can just compare your p-values. Questions about this? Before I get into questions, the whole purpose of this is to basically test whether something is roughly normally distributed, which is going to be important for our project coming up. Okay, now any questions? All right, okay, so this is a one sample KS test. So the fact that I specify that as one sample kind of alludes to the fact that there is a two sample KS test. Slightly different. The two sample KS test just tests whether two samples were drawn from the same population or two identical populations. So basically, are the distributions of two different samples similar or different? So hypotheses, the null hypothesis is that there is no difference between two distributions. And the alternate hypothesis is that the two distributions are different. So this is the setup of our hypotheses. We know we're going to do a two sample KS test, and we set our alpha at 0.05. The D statistic is actually calculated the exact same way. So instead of in this graph, instead of one being the normal distribution and one being the sample that we're testing, each line is going to represent the CDF of a sample. And if the samples are similarly distributed, then you can imagine that the CDFs will be, following each other pretty closely throughout. But if not, you'll get a fairly large D statistic, which you will use to compare with this two sample D table. So the only thing to note is that it is a different set of critical D values. But basically, there is a page over here that you can figure out, okay, based on the number of observations in each sample, you might get a different D statistic. And then there's a bit of calculation that you have to do, but not super important for us because we can do this in SciPy as well. And then basically, again, you can compare the p-value using SciPy, but if not, just look for a larger D value to mean that the two samples are differently distributed. Cool. Any questions about this? All right, we're getting through this pretty quickly. One last test that we're going to talk about is the ANOVA test. I've also attached some additional reading if you're just interested in learning more about the ANOVA test and where that comes from. I personally like reading this kind of stuff because it gives a lot of intuition on the math that goes behind it. Totally optional, but yeah, it's there if you want it. When do you use an ANOVA test is if you want to compare group means with regards to a single variable. So just see if there is a statistically significant difference between groups. Before I get into more explanation, just using an example to explain the situation. An example where you would use the ANOVA test is there a difference between the mean GPAs of freshmen, sophomores, juniors, and seniors? The null hypothesis is that there is no difference in the means. Alternate is that there is a difference in the means. Another example that could be relevant, something that's, I guess, relevant to your last project, you did movies and genres, right? If you wanted to see whether there is a significant difference in maybe movie revenue across different genres, you can look at that as well. Is there a difference between the mean revenues between comedy, drama, horror movies, and however many movies you want, or however many genres you want? So an ANOVA test will help you figure out whether there's a significant difference between groups. So an intuition, or one way of thinking about the ANOVA test, is sort of like you're doing a bunch of t-tests with each individual group. So in this situation, you could technically just, with the 4 school years, freshmen, sophomore, juniors, and seniors, you could just compare every pair and run a t-test per each pair. I think you'll end up doing six different t-tests, 6 different two-sample t-tests if you wanted to see like whether, is freshman different from sophomore, freshman different from junior, freshman different from senior, so on and so forth. You could do that, but it does lead to a multiple comparisons problem, which is a good statistical concept to be aware of. And mainly the reason why we prefer doing an ANOVA test straight up versus doing all of these individual t-tests. Because as we know, doing an individual t-test is a one-liner. In Python, we could technically just get all the combinations of pairs and run all of those t-tests. So to think about the multiple comparisons problem, first imagine an experiment where, let's say we're comparing freshmen and sophomores. We do a 2-sample t-test and it yields a p-value of 0.03, which is under our alpha, so great. The GPAs between freshmen and sophomores is statistically different enough. However, if we keep doing this over and over again, a p-value of 0.03 means that there is still a 3% chance that this difference that we observed just happened by random chance. If we were to keep doing this over and over again, in this case, we would do it maybe 6 times. We would do like, all the different possible pairs of those 4 years. If the probability of correctly rejecting the null hypothesis in a single experiment is 0.97, because 1 minus 0.03, if we were to repeat this over and over again, so just imagine a situation where we had to do like 100 different t-tests. The more you do this, and let's say we all get roughly the same p-value of 0.03, the probability of correctly rejecting the null hypothesis or correctly coming to the conclusion yet that, yes, there is a difference, goes down to 0.04, goes down to only 4%. If we use this like GPA example, we have 6 pairs between the 4 groups of students. And let's say each time we get a p-value of 0.03, if we do the calculation of 0.97 to the power of 4, the probability of correctly saying that there is a difference between all of the 4 groups goes down to 0.88, and it starts to go down exponentially as well. So that's something to know, and that is the multiple comparisons problem. The fact that when you're doing a bunch of experiments separately, there is a type 2 error, there's a type 1 error that is associated with each of those conclusions to those experiments. So that's what the ANOVA test gets rid of. As a quick tangent, I don't know if anyone has seen this before. I thought this was kind of funny. There is this whole concept of spurious correlations of things that just so happen to be correlated just by like random chance and just by, by no relation at all. This links to an article that I think you might have seen this in like memes or on Reddit or something. But these are just things that are completely unrelated that so happen to be correlated with each other. So that if you were running some sort of like, for example, if you're running like KS tests on something like this, you would say like, okay, yeah, the distribution of these two are the same. And you might incorrectly say that, okay, these two are coming from the same effect. So super random things like US spending on science, space, and technology seems to correlate like 99.79% with suicides by hanging, strangulation, suffocation, and all sorts of random things as well. Like crude oil imports from Norway just correlates with a 95% with drivers killed in collision with railway trains. So these are all known as spurious correlations, things that are correlated with no real causal relationship. So kind of different, but also very, very similar concept to making a conclusion based on p-value. The fact that there's still a 3% chance that the conclusion is spurious. So back to what we were talking about, doing an ANOVA test just saves us from this multiple comparisons problem. Because instead of calculating a bunch of individual t statistics, what we have here is a singular f statistic, which is over here. The formula is pretty complicated. No need to go into it, because in the next slide, I'm going to show you all what that looks like in code. But any questions about the setup of an ANOVA test so far? All right. Okay, so this is how we code out an ANOVA test. This is slightly different from all the other tests that we talked about so far. All of those are all one-liners. However, the ANOVA results, the ANOVA test, the code looks like this, and I'm going to explain why. So we're going to take a look at this data set that this is being used. This is actually from one of your labs. And let's take a look at this data set. So basically, this is about supplements and tooth growth. And so here we have tooth growth length, I think in like millimeters, I hope. And basically you have different tooth growth lengths connected to different supplements. So here we have, let me just zoom in a little bit. Here we have two different kinds of supplements. One is just called VC, the other is called OJ. And then within these as well, you have different dosages. So you have for VC, you can get a 0.5 dose, a 1.0 dose, and a 2.0 dose. And for OJ, the same thing. You can get 0.5, 1, and 2. And we're going to do an ANOVA test to see whether there is a difference in the mean tooth growth between the two different supplements and also between the different dosage levels. So that's what we're going to do our ANOVA test on. All right, why I want to go into this is because this is going to be the syntax that you're going to be using for your project. We're going to be using the stats models library to actually do our linear regression. So a couple of things here. You have your stats models alias as SM, but also we have OLS. And OLS stands for ordinary least squares, which is the method of solving linear regression. For now, don't worry too much about that. Just know that OLS is our linear regression model. If you remember what I talked about at the start of this session, where like later we're going to be predicting housing prices with features of a house, that's similar to what's being set up here. So here, the formula that they're setting up is we're trying to predict the length of tooth growth using the kind of supplement used and the dosage. So we'll get into this in more detail next week, but when you set up a linear regression, you basically want to come up with some formula to say that, okay, with this supplement and this level of dosage, we can predict your tooth growth. So that's what's being set up here. This string, and in your topic 18 labs, you'll get into this more, and also we'll do this next week. This string syntax is actually written in the language R. We don't really use R anymore, but traditionally R was used for data science a lot. I think it's still being used a lot, but more in academic sense, because now we just use Python because Python is a lot more user-friendly. But if you're curious about this syntax, it comes from the R programming language. What's happening here is we are fitting a linear regression model with this formula to our data. And DF basically is this data over here. So we're just trying to see how does length, how can you find the length as a function of supplement and dose? So you fit your model as LM. So LM is just your linear model. And then from that, you actually extract your ANOVA results from your linear regression. Right now, not important to know where that comes about or how that comes about, but just know that if you want to do an ANOVA test, this is probably the best way to do it. And then these are your ANOVA results. So from your stats model stats, you feed in, there's an ANOVA from linear model method that you feed in your linear model to. I forget what type to it. I think it's number of variables, but I forget. Anyways, these are your ANOVA results. So we were looking at the difference in tooth growth with relation to the different supplements and the different dosage levels. So let's take a look at this results table and let's break this down to see what we can conclude. So let's just look at supplement first. And if you remember, we had two different supplements. The DF here is degrees of freedom. And degrees of freedom, because there were two different kinds of supplements, there was 1 degree of freedom. Our F statistic, which I guess not super important to know what this F statistic is, calculated using the formula from the previous slide. But we have our p-value of 4.29 raised to the power of negative 4, so 0.0004. So p-value definitely smaller than 0.05. We can actually reject the null hypothesis, and therefore there is a significant difference between the two supplements that are used for tooth growth. So that's for supplement. For dose, very, very similar processes looking at it. 2 degrees of freedom because we had 3 different dosages. If you remember, there was 0.5, there was 1, there was 2. And then your F statistic is way bigger, and therefore our p-value is way smaller, raised to the power of negative 17. So an extremely, extremely small number, definitely below 0.05. So we also reject this null hypothesis that there is a difference in tooth growth based on the different dosages. So that's how you interpret ANOVA values from this output. Again, we're mainly just comparing p-value to whatever critical value or alpha that you set. All right. Any questions on any of this? This is, let me see, I'm pretty sure, yeah, this is my last slide for today. Any questions? Sweet. If you all have any questions on your own, feel free to Slack as well. I highly recommend getting in contact with your project partners if you want to start cleaning some data or coming up with a strategy on how you're going to work together over the next few weeks. I would say either start sourcing your own data or literally go and download the data set from the phase 2 project. It is already like at the bottom of your phase 2 materials. Feel free to download the data set and start doing some EDA data cleaning. I think that will it'll give you a good head start, especially when we start talking about modeling, because there'll be a lot of information all at once and you don't want to be worrying about like cleaning your data or doing your EDA when we get to that. All right.
I have a question.
Anything else? Mm-hmm.
The variable LM, could you actually plot that? Does that generate a line?
So this specifically doesn't generate a line. So LM, and we'll talk about this more next week, but LM is a model object at this point. You can plot attributes of LM, but not LM itself. But we'll talk about that more next week. Yeah. Cool. Any other questions? All right, if there's nothing else, I will talk to you all tomorrow. We're finally going to get back into some coding tomorrow. We're going to go through some examples of statistical power and how we really use that, as well as we're going to go through an A/B testing example. But as for now, maybe do your blog. Also get in contact with your project partner. That's super important. I cannot stress how important that is. Okay, Slack me if you have any questions, but I will see you all at this time tomorrow again. All right, have a good rest of your day, everybody. Bye.